Yes, you're welcome to our lesson 2 of chemical kinetics. And in this lesson, we want to continue where we stopped with the introduction that was made in lesson 1. In lesson 1, we saw what chemical kinetics is, and we say it's all about looking at the rates of chemical reactions. We also saw that rate simply means change in quantity. However, whenever we are looking at chemical reactions, the quantities that change are the concentrations of the products and the concentrations of the reactants. Where the change in concentration of products is positive, the change in concentration of reactants is negative. And we went ahead to look at some key terms that are used in the study of chemical kinetics. And one key term that we looked at is the rate law, and then the other is the rate equation. And we saw these two. One comes from the other. We said the rate law says that the rate of a chemical reaction is directly proportional to the molar concentration of the reactants, each raised to appropriate powers that are only experimentally determined. And by writing the rate law, we can come up with a rate equation. And we said, according to the rate law, rate is directly proportional to the molar concentration of reactants, each raised to certain powers. And here I chose power x. And we are saying x is only experimentally determined. And we said when we remove the proportionality sign, then rate becomes equal to a given constant, a constant of proportionality, times the concentration of the reactants, each raised to power x. And where this one is the rate law, this one is described as the rate equation. And we therefore, the rate equation comes from the rate law. So the two can be actually used interchangeably. And we say, therefore, the rate equation is simply an expression that shows the relationship between the rate equation and the molar concentration of reactants, which are raised to certain powers that are only experimentally determined. So in this lesson, we want to continue by looking at the parts of the rate equation. And the first part of the rate equation that we're going to look at is the rate constant. The rate constant, and the rate constant here is K. The rate constant is the constant for proportionality, the constant for proportionality of the relationship between the rate of reaction and the molar concentration of the reactants. That is simply what we mean by the rate constant. So if you are asked to define the rate constant, then we shall be saying that this is the constant. This is the constant of proportionality. The constant of proportionality in an experimentally determined equation. Remember, this power is only experimentally determined. So this is the constant of proportionality in an experimentally determined rate equation. Alternatively, if we make K the subject from this equation, if you made K the subject, then K will equal to the rate of the reaction over the molar concentration of the reactants raised to power x. And by looking at this way, then someone could define the rate constant differently. Rate divided by the molar concentration of reactants raised to appropriate powers. We could now form a definition from that expression and say rate constant is the ratio that this is the ratio of the rate of reaction, the rate of reaction to rate of reaction to the molar concentration, of reactants raised to appropriate powers that are only experimentally determined. We shall be understanding why I am emphasizing that are only experimentally determined. So if we are looking at the rate constant, then someone could simply say it's a constant of proportionality in an experimentally determined rate equation. Or it could be looked at as the ratio of the rate of reaction to the concentration, molar concentration. We are emphasizing molar concentration of the reactants, each raised to appropriate powers that are only experimentally determined. And that's the rate constant. Now, if you looked at the value of x, the value of x will vary depending on the equation. The value of x, what we call the order of reaction, will vary depending on the equations. Orders differ. It could be a fraction, it could be even 0, it could be any number. And that means the units of the rate constant will depend on a particular reaction. So the units of the rate constant, K, depend on the reaction, because the value x will keep varying depending on the reaction. Now, another term, another component of the rate equation that we would want to look at is now x itself, which we are calling the order of reaction. So another term is order of reaction. Order of reaction. What do we mean by order of reaction? Now, if the reaction has more than one reactant, let us assume we have A plus B, and A plus B are giving products. Now, because the rate law is concerned with the concentration of reactants, I don't even want to mind about the products. Now, from this expression, someone could be tasked to read the rate equation. If, let us say, a reactant A is balanced stoichiometrically by small a, and reactant B is balanced by B. The rate law says that rate is directly proportional to the molar concentration of the reactant C. So it is directly proportional to molar concentration of A, and also directly proportional to molar concentration of B. And each of them is raised to certain powers that are only experimentally determined. So if this is x, this would be y. The value of x and y do not come from the balanced equation, do not come from the stoichiometry. So, in this case, what we call order of reaction, because each of these powers is an order of reaction. So, order of reaction will equal to the sum of x and y. The sum of x and y. So if we are to define order of reaction for a reaction with multiple reactants, then order of reaction is the sum. Order of reaction is the sum of the powers to which each of the reactants in an experimentally determined rate equation is raised to. And we said these powers x and y are only experimentally determined. So when we are writing, we emphasize that. So we are going to say order of reaction is the sum of experimentally determined powers. The sum of experimentally determined powers to which each of the molar concentration of reactants is raised to in an experimentally determined rate equation. The sum of experimentally determined powers to which each of the molar concentration of reactants is raised to in an experimentally determined rate equation. Sometimes this type of order of reaction is called overall order of reaction. So we have the concept now of overall order of reaction. We talk about overall order, so we can say overall order of reaction. We talk about overall order of reaction in cases where the reaction has more than one reactant. So in this case, overall order would be x plus y, the sum of experimentally determined powers. But then we could talk about order of reaction with respect to a given reactant. For example, we can say that X is the order of reaction with respect to reactant A. For example, X equals order of reaction with respect to reactant A, whereas Y is order of reaction with respect to reactant B. So we have order of reaction with respect to a given reactant, but there is also what we call order of reaction. There is also what we call overall order of reaction. So if we are asked to define order of reaction, then we are going to say order of reaction is the sum of experimentally determined powers to which each of the molar concentration of reactants is raised to in an experimentally determined rate equation. However, if they say order of reaction with respect to a given reactant, then it will simply be the power that is experimentally determined raised to that reactant. So someone will say order of reaction with respect to a given reactant is an experimentally determined power to which the concentration of that reactant is raised to in an experimentally determined rate equation. So if they said order of reaction with respect to a reactant, then you will be saying that this is an experimentally determined power. It is now only one. This is an experimentally determined power to which the molar concentration of reactants, to which the molar concentration of a reactant, that reaction, to which the molar concentration of that reactant is raised to in an experimentally determined rate equation. That's what we call order of reaction. Now, apart from order of reaction, we have other terms that we can still look at, which are not reflected here, but are very crucial terms. There is now what we call molecularity, another term. Molecularity of a reaction. The other one is order of a reaction, and then molecularity of a reaction. Now, while order of reaction is experimentally determined and refers to certain spatial powers, molecularity is theoretical and only true or only known for those reactions whose mechanisms are well known. The mechanism, the procedure, the way the reaction proceeds is very known. So we can talk about molecularity. And molecularity simply refers to the number of chemical reactants. The number of chemical reactants participating in the slowest. Slowest is also called rate determining step. Of a chemical reaction, rate determining step of a chemical reaction, of course leading to formation of an activated complex. The rate determining step is the one that leads to formation of the activated complex. Remember, we are saying molecularity is only known theoretically and for reactions whose mechanisms are known. So if we know how to describe a mechanism of a certain reaction, then we know which one is the slowest step and which one is the first step. Now we are saying the slowest step is the one which determines the rate of a reaction. It is the one used to measure the rate of a reaction. And one uniqueness about it, it leads to the formation of the transition state. So how many molecules are participating in the rate determining step to form an activated complex is the molecularity of that reaction. So the number of chemical reactants, if it is 1, then the molecularity is 1. If it's 2, then the molecularity is 2. Now, unlike order of reaction, molecularity cannot just take on any values. Molecularity will take on definite numbers like 1, 2, 3, 4. Not like order of reaction, which can take on fractions and then zeros. So in the next video, we shall be now trying to look at these two terms and contrast them, and we get a better insight of molecularity versus order of reaction. Don't miss the next lesson.